Hello class, today we're going to talk about frequency distributions. This topic is pretty basic, but it's something that I want you to be able to identify, like difference between a regular frequency table, a group frequency table, know how to convert proportions to percentages. So there are a few things in this lecture that are going to be important, but for the most part it's pretty simple. All right, there are four ways that we can display frequency information about a variable. We could use frequency tables, group frequency tables, histograms. Histograms probably the most important one here, and frequency polygons. All right, so let's talk a little bit specifically about frequency tables. But first, let's talk about things very generally. So in many instances, we want to display the frequency of our scores. We might want the reader of our paper, or whoever it is that we are trying to explain the data to get some visual understanding about the distribution. If I just told you the variance was 5, you might not really know how the scores vary that much, whereas if I were to put all of this in a lovely histogram, you would get a better understanding of the data set. So part of this reason is graphical. And graphs can be more powerful than statistics, especially with the layperson. All right, in psychology, among colleagues and your peers, statistics are going to be more convincing. But if you're working in a place where someone doesn't understand statistics that much, visual representations of data are much more important. So let's say that we want to get some visual information about the degree of variability in our data set. We might use a frequency measure or a frequency distribution. Another good thing is we can identify outliers very easily, and how much outliers are messing our data by examining them in a frequency distribution. All right, what do I mean when I say frequency distribution? A frequency distribution describes the pattern of numbers of outcomes by displaying a count or proportion or percentage of each of the possible values of that variable. What's important to note here, and why what we're talking about in this lecture is different than the stuff that we're going to talk about with the visual displays of data, we're only concerned with one variable here. All right, a single variable. Whereas with a bar graph, with a line graph, we might be concerned with two variables, right? Maybe the independent variable and the dependent measure. Here we just care about a single measure. Typically, it's our dependent measure, our dependent variable, and we are interested in the frequency of the scores, okay, as opposed to what everybody in a certain condition scored. All right, so we're interested in a single variable. All right, so with these frequency distributions, they are a visual depiction that's going to show how often each value, each score occurred. So what we're going to have in these frequency tables, we're going to have one list of all of the potential scores, and on the other side, in the other column, we're going to have the frequency of each of those scores that appears in our data set. All right, it's good to first start off with a frequency table because it can easily be converted to some of the more advanced forms of showing frequency, like a histogram, like a frequency polygon. So a regular frequency table is easy to start off with. With a regular frequency data, or with a regular frequency table, we can only examine discrete data. Only look at discrete data. If we have continuous data, we would need as many categories as there are individual scores, and for a continuous data set, there are infinite amounts of scores that there could potentially be. So we couldn't do a regular frequency table for it. We'd have to use a special kind of frequency table. I'm going to go on a little bit of a tangent because your book goes on a little bit of a tangent. Describe the difference between raw scores and transformed scores. And this is something that's going to be important. Raw scores are our data before we do any kind of manipulation to our data. All right, they're the data that we immediately collect. So suppose if I were to give a 20 item test, the number of items my students got right would be the raw score. Now, a lot of times you guys don't care about, like, if you got 15 out of 20. You want me to convert that in some way to a letter grade. So the letter grade here would be our transformed score, and the raw score would be the number of items that you got correct on a test. All right. So a transformed score, this is a data point that has been altered in some way. Maybe we convert the number of items you got right on the test to a percentage. Maybe we convert it to a letter grade. There are many examples in psychology of transformed scores, but I'm going to keep with my simple grade analogy or grade example, because that's something that all of you guys are familiar with. So suppose we have a 20 question test. Our raw scores might be the total number of items you got right. We might transform this to a proportion. All right. And let's mention right now, if I take these proportions and I multiply them by 100, I'm going to convert them to percentages. So if I convert this person's score, a 16, to a 0.80, I can multiply this by 100, and that person got 80% of the questions right on that test. Seems kind of self-explanatory, but I just want to make sure that we're all on the same page here, because in the not too distant future, we're going to be converting proportions and percentages with one another. So it's important to note that right now. All right. So first of all, what does a frequency table look like? It looks like this thing right here. All right. On the left-hand side, we have the outcomes. We have the particular scores. So maybe we have something like course grades. We have A, B, C, D, and F. This has to be discrete, because otherwise we would have infinite numbers of outcomes here on the left, and that just wouldn't be feasible to do. And we have the raw frequency over here in the right column. All right, so 5 people made an A, 15 people made a B, 17 people made a C, 0 people made a D, 3 people made an F. Fairly easy to read. If we want to create a frequency table, the first step is to determine what our highest and lowest scores are. We create 2 columns. The first column is going to be the name of the variable, and the second column is going to have frequency in it. We might abbreviate frequency with a lowercase f. We're going to list the full range of values. Again, this is the full range, every single value that the variable could take. And typically we want to arrange them in some way. All right, so here I have A all the way through F, so we've got the highest scores up here and the lowest scores down here. If this was some numeric data, I'd do the same thing with the higher scores up here, the lower scores down here. You could flip them, just as long as there's some order to them. All right. Make sure that you include all the values in the range, even if nobody ended up scoring that. So no one scores a D here, but we're still going to include it in the frequency table. All right. We're going to count the number of scores for each of these values and put them in our frequency column here. And so we create a frequency table. Not too difficult. All right, a frequency distribution table indicates how many objects or outcomes of a particular type or class. If we have outcomes that are alphabetical and they're a nominal variable, we should put them in some kind of order. Maybe put them in alphabetical order, just to make it easier for the reader to find the particular outcome. All right, here's another example of a frequency table here. And instead of starting with the highest value, we're starting with the lowest value. That's perfectly fine, just as long as there is some order to the frequency table, some order to these scores. All right, number of children in a household, and here we have the frequency of each of these households that we have gotten data from. Okay, let's create a frequency table for countries and how many first or second place finishes they've had in the World Cup of Soccer. All right, here are all of the countries that have at least one first or second place finish in one of the World Cups since, when did it start? 1930, I believe. Okay, United States, not doing too bad, not too shabby. I think this data was collected at 2011. I believe we've made it back there since then. But let's just look at this data. All right, so if we were to look at the total number of first and second place finishes for all the countries, we would see that the vast majority of them have never been to the finals of a World Cup. There are a few people that have had one-time appearances or two-time appearances, and very few countries have had more than that. Okay, the country that has had the most second or first place finishes, you might take a guess. I thought it was Brazil, but it actually ends up being Germany here. Brazil's right here with 8 appearances. I don't think Brazil puts as much into their women's soccer team compared to Germany. Let's see if I'm right about that. Brazil, all right, 1 appearance of the women's, but for Germany we see good even distribution across the men's and women's soccer teams. All right, so we might not just want to put the raw frequency. The raw frequency is good, but we would need to know something about the total number of people or the total number of outcomes. So this 5, that doesn't tell me if it's 5 out of 5. That doesn't tell me if it's 5 out of 20. It doesn't tell me if it's 5 out of 100. That 5 is only going to make sense if I know how many total people were sampled, how many total people are in my data set. So what we might do is we convert the frequency to a relative frequency and create a relative frequency table. Now the relative frequency table can have 2 things in it. It can have the proportion, or it can have the percentage of the total number of people. Okay, how do we calculate a proportion and a percentage? Well, to first calculate a proportion, what we do is we take the frequency and we divide it by the total number of subjects, or the total number of instances of data. So to calculate a proportion, we take the frequency and we divide it by n. I believe we have 40 subjects in this theoretical class here. And so to find the proportion, we would take, for A, we take 5 divided by 40, and we would get 0.125. And so then that would be the proportion. But sometimes people don't like working with proportions. They see percentages much more frequently. So sometimes we might prefer to calculate things in terms of percentages. And a percentage is a fairly easy thing to calculate from the proportion. We just multiply it by 100. So my proportion for A's was 0.125. We just moved that decimal place over 2 spots to the left. 2 spots to the left? No, 2 spots to the right. My apologies. All right, it was 0.125. We moved that decimal spot over 2 places, and we get 12.5% of people made an A. 37.5 people made a B. So it's easy to go from a proportion to a percentage. You just multiply it by 100. It's easy to go from a percentage to a proportion. You just divide the thing by 100. Again, make sure that you're comfortable with these kind of calculations. So relative frequency, that's good. Sometimes that's going to be more useful than the raw frequency. But there's some other kinds of frequency that we might include in a frequency table as well. We might want the cumulative frequency. Here what we're going to do is we start off with our lowest score, and we see how many people got in our lowest score. And then we're just going to add things on top of it till we get to the highest score, which is going to contain everybody. So we have 3 subjects that made an F, so for cumulative frequency we have a 3. Nobody made a D, so that's still going to be a 3. 17 people got a C, so we add 3, which is what we had beforehand, to that 17, which is going to give us 20. For B's, we have 15, so we're going to add 20 to 15, and so the cumulative frequency is going to be 35. This is good for calculating things like percentiles, like are you in the upper 10%, are you in the top 25% of your class. So sometimes we might want to include cumulative frequency. Sometimes we might want to be super fancy and include the cumulative relative frequency. So instead of just adding up the cumulative scores here, all the raw frequencies. We might add up all the proportions or add up all the percentages. And that's what we have here. All right. We of course grade, we have the relative frequency, and we add the relative frequency as we go higher in these scores. All right. So for instance, if you made a C, right, you're in the 50th percentile. Half the people scored above you, half the people scored below you. And that's how we would go about interpreting that, right? So are you in the top percent of your class, top 10% of your class? You would have to look at something like a cumulative relative frequency table. Oh, that's a mouthful to do something like that. All right. I'm never going to get you to calculate one of these things on your own, right? Your handwriting is probably like mine, not that good. We're going to get the computer to calculate these things for us. So that's going to be a whole lot simpler. Excel and SPSS can do these like that. All right. So those are our regular basic frequency tables. And again, remember that the only kind of data that we can display using a regular frequency table are discrete variables, variables that there are a finite amount of values that they can take. Suppose we have continuous data. What do we do for continuous data? Well, we can create a grouped frequency table. A grouped frequency table, instead of having one outcome, one particular score on the left-hand side of the table, we have a range of values. So we can see how many people scored between a 55 and a 59.99 here. So same thing as a frequency table. The only difference here is that we have an interval on the left-hand side as opposed to one specific value. All right, we can use group frequency tables for both discrete and continuous variables. But the only thing that we can use for a continuous variable in terms of frequency tables is a group frequency table. All right, so this interval here looks like it's a continuous variable. So we couldn't list every single value that this interval might, or these scores might end up taking. It would not be very useful for us. And sometimes for discrete variables, if there's just too many potential categories and it would create a really, really awful looking frequency table, we might group the frequency table. All right, how do we create a grouped frequency table? We're going to first find the highest score and then the lowest score. And then we're going to make a decision about how many bins we want, okay? I want you to remember that word bin. Okay, how many of these intervals we want? Intervals or bins. Bins is the term we're going to use when we use SPSS. All right, so we're going to find the full range of the data. We're going to determine the bin size, the number of intervals, and the best interval size. We're going to figure out the number that will be on the bottom and the number that will be on the top. And then we're going to create all of these intervals and then record the frequency of the scores within each particular interval. Like I said, SPSS will do this fairly quickly for us. Here's an example of us collapsing a regular frequency table into a group frequency table. Maybe it's the case that these are too many potential scores and this frequency table is too large. So we might collapse it. So we have 0 to 2 children, 3 to 5 children, 6 to 8 children. If we end up collapsing, we want to make sure that the interval size is consistent. We don't want to change the interval size like this is 0 to 4, this is only 5, and this is 6 to 8. That would be weird and it would be hard to interpret. So we want to make sure that the interval size is consistent throughout our group frequency table. All right. The only exception for this is if we want to include at the very bottom or very top the highest value or the lowest value, and we want to say below a certain score or above a certain score, we can do that at the extremes of our group frequency table. And just like regular frequency tables, we can have the raw frequency, we can put in the relative frequency, we can put in the cumulative frequency or the cumulative relative frequency, right? So we can use any of those permutations, just any version of frequency that we want to include. All right, By far, the most frequent way that you're going to see frequency data is via a histogram. A histogram is going to look very similar to a bar graph, and you're going to think that it's a bar graph, but it is not. A bar graph is showing us data on two variables. Maybe it's our independent variable and people's score on the dependent variable. A histogram, on the other hand, displays information about just one variable, and the information that it's displaying is frequency. All right, so for a histogram, on the x-axis we have the scores, and on the y-axis we have frequency. Here's some examples. So here we have the heights of black cherry trees. We have our intervals here on the x-axis, the height in feet that these trees will eventually grow to. And we have the raw frequency for here on the y-axis. So for histogram frequency, this could be raw frequency, this could be relative frequency, all of that information on the y-axis. Typically, you won't see cumulative frequency. You'll see either relative or raw frequency on the y-axis. And then our scores, our dependent measure, our variable of interest is going to be on the x-axis. The thing that I want you to pay attention to is that these bars are touching one another. That's a hallmark sign that we're dealing with a histogram and not a bar graph. To do these graphs the best way, histograms should always, the bars should always be touching. For a bar graph, they should never be touching. Now, some people break that rule, and it might make things confusing. But just try to remember that graphical difference, and that will help you out in trying to figure out what kind of graph you're looking at. So the good thing about a histogram is that we can get some idea about what our distribution looks like. We can see if our distribution is skewed. We can see if our distribution looks normal. We can see if we have any outliers. All right. So here it looks like relatively normal. Right, we've got that beautiful bell-shaped curve. Here, maybe this is an outlier. Again, we'd have to check that out, but it seems relatively normally distributed. Okay, here we have students and their scores on a test. The average grade here is like in the 50s. That's probably not a good test, but it's normally distributed. As a psychologist, a normal distribution makes me really happy, but if a distribution on a test in a class ever looked like this, the students would not be very happy. All right, so here's just some examples of some histograms, right? Notice the bars are all touching one another. On the y-axis, we always have frequency. Again, this could be raw frequency, this could be relative frequency, and our dependent measure, our variable of interest, is always on the x-axis. All right, and along those lines, the vertical axis is also called the y-axis. All right, you guys know this, you've had it in math before. Another word that we can use for the y-axis is the ordinate. When I say the ordinate, that is the y-axis, this is the vertical axis. It's always going to show some measure of frequency. Regular frequency, relative frequency, again, the proportions or percentages. Cumulative frequency, although I see that less frequently for histograms, and cumulative relative frequency. The horizontal axis, also called the x-axis, also called the abscissa. All right, I've bolded the words that might be unfamiliar with you. All right, so when you draw this, when you use any of these, like a coordinate system, I mean, you guys do this in math all the time. These words originally come from René Descartes, the famous philosopher and mathematician. It's kind of interesting, the history of that, but interesting probably for me, not for you guys. All right, so the bars in a histogram should be touching one another. This helps us distinguish a histogram from a bar graph. All right, here's another example of a histogram. This histogram has a lot of different bins. All right, the bin size is, or the number of bins is massive here, right? There's many, many different bars. This is response time in minutes when someone tweets at an airline that there's a problem. This is how long it takes the airline to respond to that Twitter message. How would we describe this data? Again, this is kind of review. Is it, does it have a problem with skew? Yes. All right, we've got outliers off to this side. All right, it seems to be skewed. And what kind of skew is this? The tail tells the skew. So the tail is to the right, so we have positive skew here. All right, most of the Twitter messages when someone tweets out, hey, my airline's messed up, take place right away, but some of them take a longer time. Another good example here where we're looking at distributions, here we have, this is relative frequency here on the y-axis, and we have the difference between young adults and older adults, and this is reaction time to a lexical decision task. A lexical decision task is I show you a string of letters, maybe it is M-O-N-K-E-Y, and you have to tell me as quickly as possible if that's a word. M-O-N-K-E-Y is monkey, so obviously that's a word. You'd say yes. But how about if I had the string of letters Plysium, P-L-Y-S-I-M? That it does not form a word, so you have to say no. Sounds really dumb, but cognitive psychologists are able to tell a lot of important information from this task. In fact, my very first experiment dealt with the lexical decision task. We have the differences between young and older adults here. One thing that I want you to notice is that the mean is obviously different between older and younger adults, right? The mean here is probably around 500 milliseconds. The mean here is probably around 600, 700 milliseconds. So there is a mean difference here that we can tell from this distribution. But the older adults distribution is more skewed than the young adults distribution. The older adults have more outliers to their reaction time than the young adults do. And you might be thinking to yourself, why should I care? But there's a lot of research using this task and showing that the number of times that older adults have an outlier, or this part of the distribution, the amount of skew that they have, is a good predictor of which older adults are going to suffer from cognitive decline later on in life. In fact, some research at the Washington University in St. Louis, they look at this skew in an older adult's reaction time distribution, and this amount of skew does predict who's likely to suffer from Alzheimer's disease later on in life. So RT distributions seem dumb, seem like they're not very important, seem like it's pretty esoteric, but we can tell a lot of important information from them. All right, I probably know way more about RT distributions than you guys ever wanted to know, and there's some dry readings out there. Here we have the histogram for the World Cup, how many countries had first or second place finishes. Again, how would we describe this data? Okay, massively skewed, right? We would say again that it's positively skewed because the tail is going to the right here. Again, if we were trying to summarize this data, we would talk about the mode, right? The mode of 0. Okay, it's pretty dominant for this distribution. Here we have a histogram for the TV pacing index. So these people that rate TV shows went through children's programming and examined how quickly information was presented in these children programming shows. So we have raw frequency of each show, how much information does it typically present in a given amount of time. And we can see that this data is relatively normally distributed. All right, that's something that we get with a histogram. We get some idea of what the distribution of our data looks like. And sometimes this is very important. How do we create a histogram? Well, the first thing that we need to do is to get ourselves a frequency table or a group frequency table. Then we're going to draw an x-axis, and we're going to label it with our variable of interest and with the midpoints of each interval on these variables. We want to include 0 unless it's impractical, unless it just doesn't make too much sense. And we want to then draw our y-axis, label our y-axis frequency or maybe relative frequency, and we're going to include the full range of frequencies for this variable. Again, we want to include 0 if at all possible. And then we're going to draw a bar for each midpoint, centering the bar on that midpoint on the x-axis and drawing the bar as high as whatever the frequency is for that given interval. Again, an important thing if we have continuous data is to make sure that we are mindful of the number of bins, the number of intervals that we want. Because you can make the number of bins so massive that the data is kind of useless, or you can make them so small that, again, the data doesn't seem to be very useless, or seems to be very useless. Think about if we had a histogram with only 2 bars in it. It doesn't really give us a good job of what the distribution of data looks like. One thing that I want to mention about histograms that I think I passed over is what kind of data do we look at for a histogram? Typically for a histogram, our variable of interest is going to be scale. So it's going to have an interval or ratio scale of measurement. This doesn't mean that we can't do a histogram for a nominal or an ordinal variable, but we just don't see it that frequently. And again, part of the reason why we have a histogram is to get some idea of the shape of our distribution. And if our categories are picked arbitrarily and there isn't some meaning to the ordering of them like we would have for a nominal variable, the histogram just doesn't make that much sense. All right, the shape of it doesn't matter because the orderings of the outcomes is kind of arbitrary, right? So think about if we had the color of cars and the frequency of that for all UNG students. We had color cars red, black, yellow, gray, and so forth. Okay, the shape of the distribution is going to depend on which color I put in which order. And so the shape is going to not mean very much. So for histograms, typically we have a scale measure. So interval or ratio, scale of measurement. Frequency polygons. All right, so another way of displaying a histogram is instead of having these bars, we do lines. So it's kind of like the comparison between a bar graph and a line graph. So for a frequency polygon, we have a series of dots connected with lines. The x-axis represents our values, our dependent measure, our variable of interest, and the y-axis, again, in this case, represents frequency. All right, it could be either raw frequency, relative frequency, any of those versions of frequency that we talked about. So here's an example of a frequency polygon. Again, instead of having bars, okay, we have lines and dots. Now, the reason why we would do a frequency polygon, we would have to have a continuous variable. Okay, we have to have a continuous variable here and the x-axis, a continuous variable of interest. And typically we want to have a scale variable as well. So continuous and scale, and then we can use a frequency polygon. Here's another example here. So we have 2 frequency polygons on top of one another. We have the reaction time, which again is a continuous variable. And again, it is something that is a scale measure. And we have frequency polygons for an attention task when we have a large target that the subject is supposed to note and a smaller target. It makes sense that the large target is easier to identify, so the average reaction time is much quicker than that for the small target. All right, frequency polygons should only be used when the outcome measure is continuous. That's what I was mentioning earlier. All right, and here are the frequencies for our TV pacing index that I showed you a little bit earlier. The vertical axis can, of course, represent any version of frequency that we want. So this could be regular frequency, relative frequency, whatever we're interested in. The horizontal axis depicts the outcome, our variable of interest, our dependent measure. How do we create a frequency polygon? The first thing we need to do is to grab a frequency table or a group frequency table. Then we're going to draw the x-axis and label the variable of interest and include all the values for the midpoints. Then we're going to draw our y-axis, label it frequency, and include a full range of those frequencies. We're going to put a dot above the frequency for each of our intervals. And then we're going to connect the dots, just connect the dots there so that we can see the shape of that distribution. Again, why do we do a frequency polygon? It gives us an idea, a visual representation of what our distribution of data looks like. Is it normally distributed? Is it skewed? All right, where are the majority of our scores coming from? Are they coming from this interval or that interval? That's what we get with a histogram or frequency polygon. All right, fairly simple lecture. I hope it made some sense. I promise some of the stuff we're going to do in the future is much more fun than this, or at least much more fun for me. And that's what ultimately what's important, right? Haha, joke. Okay, so you guys have a great day, and I will talk with you later.